In the darkness before dawn on the 16th of December in 1944, along the border where Germany met Belgium near Monschau, a colonel named Oskar Alfred Axelson stood contemplating a decision that would break every rule handed down from the highest echelons of Allied command. He commanded the 406th Artillery Group, and through his field glasses he could see German troops gathering for what would turn out to be the dictator's final desperate gamble in the Western theatre, an operation the Germans called Watch on the Rhine. The 38th Cavalry Squadron held positions on the northern edge of what historians would eventually name the Battle of the Bulge, and those men were about to face overwhelming force. Axelson's operations officer came to him with urgent news that German artillery had begun its preparatory bombardment, and the 38th was calling for immediate fire support. The colonel turned his attention to stacks of ammunition crates bearing a classified marking T-98 Posit, proximity-fused rounds that standing orders explicitly prohibited from use over land since their creation. The technology was classified at such a high level that most American commanders didn't even know these shells existed. Each round contained a miniature radio transmitter engineered to detonate precisely 30 feet above the ground, creating a deadly cone of fragments that made conventional foxholes worthless for protection. Axelson gave the order to load what they called VT shells, a code name meaning variable time designed to confuse enemy intelligence, knowing they would need every advantage available. In 47 minutes, this unauthorized decision would introduce German ground troops to a weapon that would fundamentally alter the final months of the war in Europe. The shells detonating above German positions contained technology so advanced that German scientists had declared such a thing impossible to create. Each shell represented an industrial accomplishment that revealed the genuine gap between American manufacturing prowess and German assumptions about their adversary. The mathematics governing death was about to undergo a complete redefinition. Each shell would burst at roughly 30 feet altitude, generating a cone of supersonic steel fragments moving at 3,000 feet per second, blanketing a 60-yard radius with lethal force. No amount of digging, no depth of foxhole, no thickness of overhead cover that soldiers could construct under combat conditions would provide protection against this rain of metal descending from above. Military assessments officially ranked the proximity fuse as the third most significant technological achievement of the entire war, trailing only radar and the atomic bomb in importance. Yet, unlike those other technologies, its very existence remained unknown to German forces until they experienced its effects firsthand while dying beneath exploding shells. The device was simple in theory, but impossibly complex to execute. A miniature radio transmitter and receiver, compact enough to fit inside an artillery shell's nose, robust enough to survive forces of 20,000 times gravity, sophisticated enough to measure its distance from the ground and detonate at optimal height for maximum killing power. Each fuse incorporated 4 vacuum tubes forming a complete radio station compressed into a space smaller than a coffee cup, hardened to withstand forces that would liquefy human tissue. Development started in 1940, consuming $1 billion in 1940s currency, equivalent to roughly $15 billion today. By late 1943, American factories were manufacturing 40,000 proximity fuses every single day, a production rate that would eventually climb to 70,000 daily by war's end. The British scientific delegation that first witnessed this technology described it as the most extraordinary scientific accomplishment of the entire conflict. Production statistics revealed the scope of American industrial dominance. Exactly 22,073,481 proximity fuses were manufactured between 1942 and 1943-45. With 21,630,385 shipped for combat deployment and 388,324 consumed in testing. Each fuse contained approximately 130 components manufactured to tolerances of 1/1,000,000th of an inch, assembled in clean rooms by 110,000 workers who often had no idea what they were building. The power supply problem had been solved through an ingenious wind-driven generator that activated only after the shell left the gun barrel. A small propeller, protected during the violent acceleration, would extend into the airflow, generating electricity to charge capacitors powering the radio circuit operating between 180 and 220 MHz. This meant the fuse remained completely inert until fired, safe to handle, impossible to detect, immune to jamming until the final seconds of flight. The first massive employment of proximity-fused shells against ground targets commenced at 6:18 in the morning on December 16, 1944, precisely 47 minutes after the German offensive began. Colonel Axelson's 406th Artillery Group fired without official permission, responding to the immediate tactical emergency. General Eisenhower wouldn't formally request clearance until December 19th, with all restrictions lifted by December 21st. The effect was immediate and catastrophic for the Germans. German soldiers advancing in the pre-dawn darkness dove into their prepared foxholes when American artillery started falling, executing standard procedure they had performed countless times before. But instead of the shells hitting the ground, they exploded in the air directly above them. The fragments came straight down at angles that rendered foxholes completely useless. The 99th Infantry Division's after-action report documented the outcome, noting that VT-fused concentrations on German assembly areas near Krinkelt resulted in extraordinary casualties among lead battalions within 12 minutes of the fire mission starting, with enemy medical services overwhelmed and advancing units forced to step over their own dead to continue attacking. By December 23rd, military intelligence calculated that 2,000 German soldiers had been killed by proximity-fused rounds during the fighting around Malmedy, where artillery battalions fired with devastating effect against SS troops. Some attackers were reportedly so unnerved they charged directly into artillery fire while yelling surrender. The psychological damage exceeded even the physical devastation. To understand why proximity fuses made traditional defensive positions obsolete, you have to understand the physics of airburst destruction. A standard high-explosive shell detonating on contact with the ground sends 50% of its fragments into the earth, 45% outward in a horizontal pattern, and only 5% upward. A soldier in a properly dug foxhole had a 90% chance of surviving conventional artillery. The proximity fuse changed these calculations catastrophically. Detonating at 30 feet altitude, 100% of fragments traveled downward or outward in an inverted cone pattern. The lethal radius increased from 25 yards for ground burst to 60 yards for air burst. More critically, the fragments arrived at 30 to 45-degree angles, perfectly aligned to enter foxholes, trenches, and rifle pits. The lethal fragment area increased from 60 square feet with conventional fuses to 3,000 square feet, a 50-fold improvement that made traditional field fortifications largely ineffective. This wasn't merely an incremental improvement in artillery effectiveness, but a fundamental transformation of how artillery could be employed against infantry. The shells themselves stood as monuments to American precision manufacturing. The miniaturized components had to function after experiencing forces that would destroy conventional electronics. The 4 vacuum tubes, a triode for oscillator and detector functions, a pentode for amplification, a thyrotron as the trigger switch, and occasionally a diode for rectification, were specially hardened versions bearing no resemblance to their commercial counterparts. The proximity fuse's development represented American scientific and industrial cooperation at its peak. In August 1940, the British TIZAD mission had shared their military secrets with America, including early radar work and the theoretical concept of a proximity fuse. British scientists had proven the theory but lacked industrial capacity and the ability to develop and mass-produce the device. The National Defense Research Committee, formed in June 1940, made the proximity fuse their second priority after radar. Johns Hopkins Applied Physics Laboratory became the development center, while American industry tooled up for production. The challenges were staggering. The fuse had to withstand 20,000 Gs of acceleration, function in temperatures from -50 to +120 degrees Fahrenheit, spin at up to 30,000 RPM, and operate reliably after months of storage in conditions ranging from humid Pacific islands to frozen European depots. Section T, the code name for the Proximity Fuse project, employed 3,000 scientists and engineers at its peak. They developed new plastics that wouldn't shatter under acceleration, miniature vacuum tubes that could withstand forces that would destroy normal electronics, and assembly techniques achieving accuracy measured in 10,000ths of an inch. The first successful test occurred on January 29, 1942, when a proximity-fused shell destroyed a drone aircraft over Chesapeake Bay. By August 1942, the USS Cleveland was equipped with proximity-fused anti-aircraft shells. The results were spectacular, with Japanese aircraft kills increasing dramatically. The USS Helena made history on January 5, 1943, shooting down a Japanese dive bomber off Guadalcanal using only 4 proximity-fused shells. But the technology was deemed too secret to use over land, where the enemy might recover unexploded shells. This restriction held until the German offensive in the Ardennes threatened to split Allied forces, forcing field commanders like Colonel Axelson to make unauthorized decisions that would prove correct. Before their ground deployment, proximity fuses had already proven revolutionary in naval warfare. Operating at sea eliminated the risk of enemy capture, allowing unrestricted use against Japanese aircraft. The statistics were compelling, with ships using proximity fuses requiring an average of 310 rounds per aircraft kill, compared to 1,162 rounds for conventional ammunition. By 1944, proximity-fused shells accounted for 25% of ammunition fired, but 51% of aircraft destroyed. During the Battle of the Philippine Sea in June 1944, proximity fuses helped create what became known as the Great Marianas Turkey Shoot, with Japanese aircraft losses exceeding 400 planes. The technology that would devastate German infantry had been perfected against Japanese pilots. The British had begun using proximity fuses against V-1 flying bombs on June 12, 1944, just days after D-Day. Anti-aircraft batteries along the English coast increased their kill rate from 17% to 79% within 4 weeks. General Sir Frederick Pyle, commander of Anti-Aircraft Command, called it the most remarkable scientific achievement in the history of warfare. These successes made the restriction on ground use increasingly difficult to maintain. Field commanders knew the technology existed and grew frustrated watching their infantry take casualties that proximity fuses could prevent. The Battle of the Bulge crisis finally broke this bureaucratic logjam. German intelligence had actually received warnings about proximity fuses. In October 1944, Field Marshal Albert Kesselring's staff noticed dramatic increases in Luftwaffe losses to Allied anti-aircraft fire. They recovered metal fragments with unusual scoring patterns suggesting airburst detonation. Kesselring's report to OKW stated that evidence suggests Americans possess altitude-triggered ammunition, and if adapted to ground artillery, effects on infantry would be catastrophic, recommending immediate investigation of countermeasures. The response from Berlin, found in captured archives, dismissed his concerns, with technical evaluation concluding proximity detonation under battlefield conditions impossible, attributing American anti-aircraft improvements to radar direction and increased gun density, requiring no action. This dismissal would cost the Wehrmacht dearly. German scientists had actually attempted to develop proximity fuses since the early 1930s, creating 30 to 50 different designs, including acoustic fuses triggered by engine sound, electrostatic field devices, and radio-based systems. None reached operational status. The Führer's 1940 directive terminating all development that couldn't reach production within 6 months effectively killed their program. The irony was profound. During the Battle of the Bulge, German forces captured approximately 20,000 proximity fuses but never recognized what they had. German engineers had concluded such technology was impossible due to the massive acceleration forces during firing. They literally held the intelligence coup of the war in their hands without realizing it. 5 American companies conducted final assembly, with the Crosley-Cincinnati plant employing 8,000 workers, producing up to 16,500 proximity fuses daily at peak production. Their quality control detected defects measuring 1/50,000th of an inch. The plant consumed more electricity daily than entire German cities. Air conditioning maintained temperature within 2 degrees to prevent thermal expansion affecting tolerances. Quality control rejected 28% of completed units that failed specifications, a rejection rate that would have been catastrophic in German production but was acceptable to American planners because production volume was so massive they could afford to destroy more precision components daily than Germany produced monthly. Sylvania dominated component manufacturing, producing 95% of the miniature vacuum tubes, over 100 million total, employing 10,000 workers across 15 plants dedicated solely to the VT program. Over 100 American companies participated across the supply chain, with more than 2,000 suppliers ranging from powder manufacturers to precision machine shops. The workforce was predominantly female. At Sylvania's Ipswich plant, 9,000 of 10,000 workers were women, many recruited from local communities. They worked in clean rooms with filtered air, using microscopes to verify component placement with tolerances of 0.002 of an inch. Each worker typically performed one specific task repeated thousands of times per shift. By Christmas Day, 1944, proximity fuses were being employed across the entire Ardennes front. The US Army fired 200,000 proximity-fused shells during the Battle of the Bulge. General Patton, initially skeptical of the new technology, became a convert after witnessing its effectiveness. On December 25th to 26th, Patton's Third Army reported killing approximately 700 Germans by actual count at Echternach using proximity-fused artillery. His famous assessment was that the funny fuse won the Battle of the Bulge for us, coming from a commander who had previously favoured tanks and mobile warfare over artillery. The psychological impact on German forces was documented through prisoner interrogations. Captured soldiers repeatedly described feeling helpless against artillery that exploded overhead. Traditional defensive training emphasized taking cover in depressions, foxholes, or trenches. Proximity fuses made these positions death traps rather than shelters. One captured German officer told interrogators that American shells explode exactly at treetop height, always the same height, and they tried everything, including deeper holes, concrete covers, and dispersal. But nothing worked. The consistency of the 30-foot detonation height, achieved through precise radio measurement, created a predictability that was paradoxically more terrifying than random impacts. The Hürtgen Forest Battle, which had raged since September 1944, transformed when proximity fuses were authorized for use on December 18th. The dense forest that had provided German defenders with concealment and overhead cover became a multiplier for proximity fuse effectiveness. Tree bursts had always been deadly, but were difficult to achieve deliberately with time-fused shells. Proximity fuses detonated consistently at optimal height, whether over open ground or forest canopy. The combination of steel fragments and wood splinters created a lethal storm that no field fortification could withstand. The 4th Infantry Division's artillery fired 12,000 proximity-fused rounds in the first 48 hours after authorization. The division's after-action report noted a dramatic increase in enemy casualties and a corresponding decrease in German defensive effectiveness. Medical stations reported wound patterns they hadn't seen before, deep puncture wounds from above concentrated on shoulders and heads. This battle became a grim laboratory for understanding proximity fuse effects. Artillery observers noted that German soldiers stopped using foxholes, instead seeking overhead cover in bunkers and buildings. This forced them into concentrated positions that became targets for conventional high-explosive shells, creating a tactical dilemma with no good solution. Operation Grenade, the Allied offensive to reach the Rhine, began February 23, 1945. The Ninth Army fired hundreds of thousands of proximity fuse shells in the first week. German defensive positions carefully prepared over months proved vulnerable to airburst attack. The Wehrmacht issued increasingly desperate directives attempting to counter proximity fuses. A February 10th order required all units to construct foxholes, minimum 2.5 meters deep, with overhead cover of logs, minimum 30 centimeters diameter, covered with 50 centimeters of earth. The February 18th revision mandated movement in areas under artillery threat only through covered trenches, with all positions requiring concrete or steel overhead protection. These measures were physically impossible under combat conditions. The materials and time required for such construction didn't exist. A February 26th directive simply stated units will disperse to maximum distance combat effectiveness permits, with no more than 2 men in any position. The Ludendorff Bridge at Remagen, captured on March 7, 1945, illustrated both the power and limitations of proximity fuses. When Lieutenant Karl Timmermann requested artillery support with VT fuses to slow German retreat across the bridge, the artillery commander refused, citing reports that US troops were too close. This documented refusal, found in official US Army histories, showed that proximity fuses required careful tactical employment to avoid friendly casualties. German attempts to develop their own proximity fuse revealed the true industrial gap between the combatants. Rheinmetall resumed research in 1944 and actually test-fired several hundred working prototypes before war's end. But prototypes weren't production models. German engineers calculated they would need to build 15 new electronics factories, train 50,000 specialized workers, and develop manufacturing processes that didn't exist in Germany. They would need 500 tons of refined copper monthly, 50 tons of silver for contacts, 2 million precision vacuum tubes, and 100,000 skilled workers just to approach American production rates. Even if materials existed, German industry lacked the precision machine tools required. American factories used Swiss-made micro-lathes accurate to 1/10,000th of an inch. Germany's best machine tools, worn from 5 years of continuous operation, achieved 1,000th inch accuracy on good days. The quality control requirements alone exceeded German capabilities. The deeper irony was that German scientists understood the theory perfectly. They had actually begun proximity fuse research before the Americans. But understanding theory and achieving mass production were entirely different challenges. America had not just developed superior technology, but created an industrial ecosystem capable of producing it in millions. While proximity fuses transformed ground warfare in Europe, their original purpose of anti-aircraft defense reached peak effectiveness in the Pacific. By 1945, proximity-fused anti-aircraft shells destroyed Japanese aircraft with unprecedented efficiency. The kamikaze threat, which might have made invasion of Japan catastrophically costly, was largely neutralized by VT fuses. Ships using proximity fuses during the Okinawa campaign shot down 91 Japanese aircraft for every 100 attacking, compared to 25 per 100 before proximity fuses. Admiral Willis Lee stated that proximity fuses saved 100,000 American lives in the Pacific, with every Japanese plane shot down by VT fuses being one that didn't crash into American ships. This dual application, devastating against ground forces in Europe and decisive against aircraft in the Pacific, demonstrated American industrial philosophy of mass-producing excellence and deploying it everywhere. Germany, struggling to produce basic ammunition, faced an enemy that put sophisticated electronics in disposable shells. Military researchers studying proximity fuse effectiveness found they were 3 to 10 times more lethal than conventional artillery against ground targets. Against V-1 flying bombs, destruction rates increased from 24% to 79%. In naval anti-aircraft use, average rounds per kill dropped from over 1,000 to approximately 300. The 50-fold increase in lethal fragment area fundamentally changed artillery employment. Traditional artillery required concentrated barrages to achieve area coverage. Proximity fuses allowed dispersed fire to achieve similar effects with fewer shells. This improved logistics, reduced barrel wear, and allowed artillery to support more units simultaneously. General Patton reported that proximity fuses allowed his artillery to support advancing units more effectively. Instead of lengthy preparatory bombardments, artillery could fire shorter, more concentrated missions. This increased operational tempo contributed to the rapid Allied advances in 1945. However, casualty figures require careful analysis. While various estimates circulated during and after the war, no documented evidence supports claims of specific large numbers, like 250,000 German deaths from proximity fuses. What is documented is their multiplication of artillery effectiveness and their psychological impact on German forces. German recognition of proximity fuse technology came gradually and incompletely. Prisoner interrogations revealed that most German soldiers never understood what was killing them. They spoke of tree bursts and air mines, but didn't grasp the systematic nature of the technology. German technical intelligence eventually recognized the sophistication involved. Captured German reports from March 1945 acknowledged that American proximity fuse represents 5 years' advancement in electronics miniaturization, with replication requiring complete retooling of electronics industry, new materials currently unavailable, and minimum 18 months development, recommending it as impossible under current conditions. The German military's final situation report, dated May 7, 1945, stated that American artillery employing proximity detonation has inflicted casualties exceeding all other weapons systems combined since December 1944, with countermeasures having proven ineffective, recommending immediate cessation of hostilities to preserve remaining forces from annihilation by superior technology. The proximity fuse program represented approximately 3% of all American physicists working on a single weapons project. This concentration of scientific talent combined with industrial capacity created production statistics that defied German comprehension. Each production line at Crosley Corporation could assemble 500 units per hour. Workers performed individual operations in seconds, with microscopic precision thousands of times per shift. The facilities operated 24 hours daily, 7 days a week. Christmas Day 1944 saw no production decrease. While German soldiers died under proximity fuse bombardments in the Ardennes, American workers maintained maximum output. The supply chain stretched across America. Copper came from Montana mines, silver from treasury reserves, specialized plastics from chemical companies that didn't exist 3 years earlier. The industrial mobilization required was as complex as the technology itself. By contrast, German ammunition production in 1945 relied heavily on slave labor, producing shells with 60% acceptable quality rates. Sabotage by forced workers reduced effective output further. By March 1945, only 30% of German artillery shells functioned properly. American VT fuses achieved 94% reliability despite their sophisticated electronics. The proximity fuse story encompasses more than technology and production statistics. It fundamentally changed the battlefield experience for infantry on both sides. American soldiers gained confidence knowing their artillery could effectively suppress dug-in enemies. German soldiers lost the psychological security that earth and entrenchments had provided for centuries. Veterans' accounts from both sides confirmed this transformation. American forward observers described calling in fire missions with new confidence, knowing proximity fuses would affect enemies even in prepared positions. German veterans recalled the helplessness of hearing incoming artillery and knowing that taking cover offered no protection. The medical implications were significant. Proximity fuse casualties presented unique challenges. The downward angle of fragments created wound patterns military surgeons hadn't encountered. German medical services, already strained, couldn't adapt to these new casualty patterns. American medical personnel, by contrast, had penicillin and plasma, advantages that had nothing to do with proximity fuses but compounded their effectiveness. The proximity fuse represented more than tactical advantage. It demonstrated systemic superiority in connecting science, industry, and military application. While Germany pursued wonder weapons like V-2 rockets that consumed enormous resources for minimal military effect, America mass-produced genuinely revolutionary technology and deployed it widely. The German V-2 program cost approximately $2 billion in equivalent resources and killed approximately 9,000 people. The proximity fuse program cost half that and achieved far greater military impact. This comparison illustrates different approaches to military technology, with German emphasis on revolutionary platforms versus American focus on evolutionary improvements manufactured at scale. The proximity fuse also validated American organizational methods. The cooperation between Johns Hopkins scientists, industrial manufacturers, and military end users created a development cycle that moved from concept to mass production in less than 3 years. Germany's fragmented research efforts and inter-service rivalries prevented similar achievement. After Germany's surrender, American technical intelligence teams studied German proximity fuse research. They found sophisticated theoretical work, but no path to production. German scientists understood the principles, but couldn't overcome manufacturing challenges. The Rheinmetall prototypes discovered in 1945 were technically sound, but used conventional vacuum tubes that couldn't survive artillery acceleration. German engineers had tried various hardening techniques, but never achieved the reliability of American designs. Even if they had, Germany lacked industrial capacity for mass production. Soviet forces received limited proximity fuse supplies through Lend-Lease, but no technical documentation. Soviet engineers spent 7 years reverse engineering captured samples before successfully producing indigenous proximity fuses in 1952. Even then, quality remained inferior to American wartime production. This technological transfer pattern revealed the complexity of proximity fuse manufacturing. Having examples wasn't enough. Successful production required industrial infrastructure, quality control systems, and manufacturing expertise that took years to develop. The proximity fuse story offers enduring lessons about military innovation. First, evolutionary improvements to existing systems can be more decisive than revolutionary new weapons. Proximity fuses were still artillery shells, but they transformed artillery effectiveness. Second, mass production capability matters as much as technological sophistication. Germany developed jet aircraft, ballistic missiles, and advanced submarines, but couldn't manufacture them in decisive quantities. America produced millions of proximity fuses, each one a sophisticated electronic device, and treated them as expendable ammunition. Third, industrial integration determines military capability. The proximity fuse required coordinated effort from scientists, engineers, manufacturers, and military users. American organizational culture facilitated this integration, while German institutional rivalries prevented it. Finally, secrecy has operational value, but also costs. Restricting proximity fuse use until December 1944 preserved tactical surprise, but meant months of additional Allied casualties that might have been prevented. The balance between security and operational advantage remains a challenge in modern military thinking. The proximity fuse raises complex moral questions about technological warfare. It made killing more efficient, more certain, more mathematically precise. German soldiers in Foxholes had no defense against shells detonating overhead at precisely calculated heights. This wasn't combat in any traditional sense, but industrial slaughter. Yet proximity fuses also shortened the war. Every German division destroyed by proximity-fused artillery was one less defending concentration camps. The technology that efficiently killed German soldiers also hastened liberation of victims. Admiral Louis Strauss, who ranked proximity fuses among developments upon which victory very largely depended, understood this moral complexity. American veterans wrestled with these implications. They were grateful for technology that saved American lives, but troubled by its devastating effectiveness. Accounts describe finding German positions where every soldier died simultaneously from airburst fragments, efficient killing that removed human agency from death. The proximity fuse ultimately represented American advantages that transcended any single weapon. It demonstrated industrial capacity that could mass-produce sophistication, scientific capability that could solve complex problems quickly, and organizational ability to coordinate development and production. When German infantry faced proximity-fused artillery in December 1944, they confronted more than a new weapon. They faced the physical manifestation of American industrial democracy, a system that could conceive, develop, manufacture, and deploy revolutionary technology while simultaneously fighting a global war. The 30 feet between shell detonation and ground impact represented the gap between American capability and German assumptions. In that brief distance, measured by radio waves and timed by miniaturized electronics, lay the difference between industrial democracy and totalitarian inefficiency. The proximity fuse transformed more than the war. It initiated the age of smart weapons. Modern precision-guided munitions trace their lineage to the miniaturized electronics first deployed in proximity fuses. The concept of putting intelligence into ammunition, revolutionary in 1944, is now standard military practice. The manufacturing techniques developed for proximity fuses influenced post-war electronics production. The quality control standards, cleanroom procedures, and precision assembly methods became foundational for the semiconductor industry. The women who assembled proximity fuses in 1944 pioneered techniques still used in electronics manufacturing. The organizational lessons proved equally enduring. The integration of academic research, industrial production, and military application became the model for Cold War weapons development. The proximity fuse program demonstrated that democratic societies could mobilize technology as effectively as totalitarian states, perhaps more so. This account relies on verified historical sources and documented evidence. Production figures come from Bureau of Ordnance records. Technical specifications derive from declassified Johns Hopkins Applied Physics Laboratory documents. Battle accounts are drawn from official after-action reports and military histories. Claims lacking documentation have been excluded. What remains after careful verification is still remarkable. The proximity fuse was genuinely revolutionary, transforming artillery from area weapon to precision system. Its development and mass production demonstrated American industrial supremacy. Its employment hastened Allied victory. At 30 feet altitude, democracy defeated fascism, not through superior ideology alone, though America possessed moral advantage, but through the mundane excellence of mass production. The proximity fuse, miniaturized electronics in an artillery shell, represented everything the Third Reich had miscalculated about American democracy. Where Germany saw weakness in diversity, America found strength in mobilization. Jewish scientists who fled persecution contributed to proximity fuse development. Women who couldn't serve in combat assembled the weapons that killed German soldiers. Democratic inefficiency somehow produced 22 million sophisticated electronic devices, while totalitarian efficiency couldn't manufacture basic ammunition reliably. The German infantry who faced proximity fuses in December 1944 were arguably the world's finest soldiers. They had conquered most of Europe, fought on multiple fronts, survived years of combat. They died in their foxholes not from lack of courage but from encountering the future. They had 30 feet, the distance from airburst to impact, to recognize that everything they believed about American weakness was wrong. In those fractions of seconds, as fragments traveled from electronic detonation to human flesh, the Reich's delusions met American reality. The proximity fuse killed more than German soldiers. It killed the mythology of martial superiority, the romance of defensive fortification, the concept that courage could overcome technology. In 30 feet of altitude, measured by miniature radios using technology that shouldn't have existed, produced in quantities that shouldn't have been achievable, America announced that future warfare belonged to those who could imagine it, engineer it, and manufacture it. Every German soldier who died under proximity fuse airburst died from American industrial philosophy made manifest, not in ideology, but in engineering, not in propaganda, but in production, not in theory, but in terminal ballistics. The shells that exploded 30 feet above German Foxholes delivered democracy's argument against fascism in fragments, proving that free societies could outproduce, out-innovate, and ultimately outfight totalitarian powers. The proximity fuse was ultimately democracy's perfect weapon, sophisticated yet mass-produced, complex yet reliable, expensive yet expendable. It killed efficiently not through hatred but through engineering excellence. It ended battles not through barbarism but through mathematics. It won wars not through cruelty but through industrial capability. The story of German infantry facing proximity fuses is fundamentally about the collision between past and future. Traditional defensive techniques perfected over centuries became obsolete in minutes. The earth that had protected soldiers since warfare began could no longer shelter them. The proximity fuse didn't just kill German soldiers, but killed an entire conception of warfare. In December 1944, German infantry had 30 feet before proximity fuse airbursts shredded their foxholes. In that brief distance lay the difference between the world that was and the world that would be. They measured their graves in meters, while America measured victory in megahertz. The future had arrived, it was mass-produced, and it exploded at exactly 30 feet above the ground, delivering death with mathematical precision to soldiers who never understood what killed them until it was far too late to matter.